He's an extremely accomplished teacher, and just within the last year or two, he won an award for innovation in instruction. And I think actually you guys are going to get to see a little bit of that in action today with the clickers, which is really cool. He's excellent in the classroom. The students love him here, and like I said, he's an award-winning teacher. So he's not only going to tell you about some cool stuff, he's going to tell you in a way I think you're going to really enjoy. So it's a real treat to have Tim Stelzer here. Thanks a lot, Tim.
Thank you. All right, got the mic on. Good. Thanks for coming this Saturday before Thanksgiving. I know there's lots of other things to do, but I hope you'll find it. I hope you'll find it worth your time. I was asked to give this talk a while ago, and I had a clear vision of exactly what I was going to do, and then when I got to doing it, I changed it dramatically because, but what I wanted to do is tell you, it seems very strange. We look at elementary particle physics, we look at things that are very, very small, and it seems a little counterintuitive that you need very, very, very big things like accelerators and colliders to look at very small objects. And so I'll just show you a little bit what I want to do. First, I want to tell you why it's interesting to look at things that are so small. You might think, who cares? And then I want to show you that we just have an unbelievably beautiful model. I'd say perhaps one of the nicest things in all of science. And I hope I can convey that to you. And then we'll talk more about why we need such big machines to be able to see this. And then maybe convince some of you that it's some pretty exciting things coming up. And if some of you were, I don't know, of high school age, let's say, then there's going to be some amazing opportunities for you. It's going to be a really, really exciting time coming up in the future. So that's where we want to go. I tried to get out to most of you, not a blue one. Can't have the blue one. A white one. If any of you don't have one of these, raise your hand and Kevin will come around and he'll get one to you. And I'll show you how we're going to use those in just a little bit. So, why look at things so small? And one motivation is it's counterintuitive, but it turns out that smaller is actually bigger, okay, in a very, very real sense when you're talking about energies. So I have 4 balloons up here meant to represent mechanical energy, chemical energy, nuclear energy, and relativistic energy. Each one of these is going to smaller and smaller scales. So the mechanical energy is just, you've heard a balloon pop before. Basically, the molecules just escape. And I'm going to release that energy right now for you. It's too high for me to pop, and I'm kind of a bit of a pyro. So I'm going to use this to pop the balloon. And, oh, it's kind of a long thing. And so what I'm going to do, I'm going to release this. This is mechanical energy. You're going to hear it go pop. It'll give you a feeling for the amount of energy that's available basically at the macroscopic scale, the scale where you can see these things. This is the kind of energy that's available. And you get ready. Here we go. Okay, pretty good. So that's the macroscopic scale. That's the stuff that it's never hard to convince people it's interesting to look at. That's like monkeys falling out of trees and stuff like that. So if I look at that, I'm saying the scale is about 0.1 meters. I don't know exactly. And the energy, I just did a rough calculation of how much energy was released, not from this torch, but just from the balloon going off. It was about 10 to the minus 3 joules. And to put that in perspective, I would say that would take care of running your house for about a microsecond, 10 to the minus 6 seconds. Not very long, okay? Shorter than a flash bulb going off, basically. So that's not too much. So we're going to look at smaller scales now, and the next natural small scale would be chemical energy. So this next balloon represents chemical energy, and I wanted to keep things as close as I could to the same. So this first balloon had helium in it. That's why it was floating. So I took the next closest element I could think of, hydrogen, and they're very similar. They're both light, and it's floating. But when I release this balloon, it's not going to release just the mechanical energy. It's also going to release the chemical energy because the hydrogen is going to combine with the oxygen, and things are going to happen at a much smaller scale, like 10 to the minus 10. Now, it's going to be a lot more energy. I'm going to tell you that right now. So if you don't like loud sounds, plug your ears. And if you're sensitive to heat, you might kind of shield yourself a little bit, okay? So here we go. This is chemical energy. This is when you go from 0.1 meters down to 10 to the minus 10 meters, and it's a pretty big difference. Yeah. Okay? So that was just the second balloon. We got 2 more to go here. That's chemical. The amount of energy released there was about 1,000,000 joules. And if you wanted to think about that in terms of running your house, that would keep your house going for about 15 minutes. A typical house, about 15 minutes. Obviously, that happened a lot faster here, which is why it was loud. You see, going to these smaller scales, in one case, you're just letting the electrons get a little bit closer to the proton, basically. Going to these smaller scales, bigger energy. Well, we can take the next step. Before I do it, we should do a little estimate. Let's go down to the next smaller scale, smaller than where the electrons are. Let's look at the nucleus. That's about 10 to the minus 15th meters. And what I would like to do now is play with these clickers. We're going to have a little game here. And we're going to see if you can figure out a pattern here and figure out how much energy do you think will be released if I release not the chemical, not the mechanical, not the chemical, but the nuclear energy that's inside there. It's multiple choice, so you can use this. And I want to do it in units of how long it would heat your home or light your home. 3 hours, 3 weeks, 3 years, 300 years. And so I'm going to push go here. The timer comes up. You have 1 minute. You need to figure out how to turn your thing on and then push a button and get the green light to go on. Once you do that, it means your vote's registered. And this is something we actually use for those of you considering going to class here, or those of you paying tax dollars to support the classes here. We try to use these in our large classes to keep the students awake. If you experience a small electrical shock when... No, I'm just kidding. That's the new model. We haven't gotten that going yet. Okay, so go ahead, enter your answers. You got about 20 seconds to figure it out. Oh, we're doing pretty good. We got about 60 people that have answered. That's probably close to what we have. And you got about 10 seconds left. All right, 66 is between 65 and 70. Okay, and so these are coming in. And so now you're done. So now you can try to vote, and you'll see a little red light comes on instead, just so you can see it doesn't work anymore. All right, so you can't change your vote. And now we can see what people thought the answers were down here. Most people are saying C. It's kind of a nice little study in histograms there. But most people are saying C. It's the most popular answer. And that's pretty good, because that is, in fact, the correct answer, is C. It's about 3 years. Oops, sorry. It is, in fact, about 3 years. And it turns out that we're not allowed to do that demonstration for safety reasons. But you can take it to the next logical scale, which is you can go even smaller than nuclear. So nuclear is not high energy physics. Okay, we're going to go smaller than that. That's big by our standards, is nuclear. And so we're going to go to the next higher level, and basically you can get to relativistic. And I mean, you can't say you've been to a physics lecture unless you see E equals mc squared. And I lost my laser pointer. Okay, so here's E equals mc squared. It's sort of the ultimate energy density you can have. And if you were able to release the relativistic energy, I'm also not allowed to do that demo, it would be 4 orders of magnitude larger, enough to take care of your house for 30,000 years. Okay, a very long time. So that could be some motivation why you want to look at small things. Smaller really is bigger. That, in fact, is not the motivation for most people in high energy physics. Okay, most of us don't do it because of that, but we do it for another reason. Sometimes we tell the politicians that's why we're doing it, so we can heat the houses. But we really like the idea that when you look smaller, you get simpler. Physics is really about simplicity. Kevin said, I teach a course. I teach a whole semester course that basically has one equation, F equals ma. And you see what that means, and you do algebra with it, and you can explain almost every mechanical thing that you experience can be understood with this one simple equation plus some algebra and stuff. And that's the nice idea, is that the world we live in is so is so simple and can be understood that way. And we think by looking at smaller scales, it gets simpler. In fact, if you think about it, if you look around at the world, it seems like a very complicated place. There's sort of an infinite number of different things you can see that all behave differently and seem to act very, very differently on the macroscopic scale. But if you go down and you look at the smaller scale, you can find out that all those things are actually made up of just a few hundred atoms. Well, actually, about 100 atoms, and most of them aren't even used for the things that we are looking at there. Very simple. This might seem simple, but if you go down to even smaller scale, you find out even these 100 atoms are just composed of a neutron, a proton, and an electron. It's kind of nice to think that things could be understood in such a simple, simple way, especially if you're not very smart like me. You just think, okay, it's very easy to go on that way. And so if we go back to around 1930, things are looking very good. Aside from the Depression, things are very good. You have a world where you have atoms made out of neutrons, which have no electric charge, protons, which have an electric charge, I'm just going to call it +1, and electrons, which have a negative charge, -1. Very, very pretty picture. And you have, light, you have electric forces and magnetic forces and photons, and they all kind of fit together very well. Oh, that's too bad. You can't see that, but we'll look at that again later in more detail. And things are really look pretty good. But there are a few things that don't quite make sense. And those include the protons. You have a bunch of protons together in the nucleus, very close together. They have the same charge. Why are they staying there? They should repel. Like charges repel. That doesn't seem quite right. They see there's radioactive decay. We see atoms changing and protons changing into neutrons. And we wonder what's going on with that. And as you'll see, there's some other strange things that come up as they continue to look into this. Okay, so I just had some fun playing. So we're just to get a sense of the scales. Here's looking at some flowers at about a 1 meter scale. We can zoom in on this down to 0.1 meters. We're going to zoom in some more, 0.01 meters. We start seeing the fly. We can zoom in more, get a little closer look at him. And we can get in a little closer. There's his eye. We can go closer than that. All these are huge scales by our standards, by the way. These are big, big, big to us. Don't deal with stuff this big. Go smaller, a little receptor in the eye for the thing, a little smaller, still way too big. So, DNA, huge, huge. So let's zoom in a little closer in the DNA. There's the atom, still big. So we zoom in a little closer. The nucleus, it's still too big, but now we're getting close to where we want to be. Okay, so that's a little tour forward on these things. If you want to look at things that are small, this is my favorite demo of the whole lecture. Does anybody have a large bill on them? A large bill? That would be good. Okay, there's a large bill. So you hold that bill. Can you hold it flat like this so I can see it? Perfect. Now, I see the bill. I see I want it. But I don't know the serial number on it. So if I wanted to see it in more detail, what I would do, I'd come up here, and I would take it, and I would look at it, and I'd bring it a little closer. And now I can see detail on it, and I see it's CF16619628. That's the one I lost. And so I take this bill, I bring it a little bit closer, and I can see it. And I can see it closer, and you say, well, what if I want to understand the molecules? Well, I bring it closer and closer. And, okay, now I can't see any more detail. You bring it too close, and all of a sudden your eyes can't focus anymore. So you can look at things kind of to a pretty small scale just with your eyes. If I want to go beyond that, and I forgot to get this demo, what I would need to do is I would need to take out a magnifying glass. And then I could see it in more detail. And if I wanted to look in even more detail than that, what I would do is I would take out a microscope. Seems pretty good. And then you could imagine getting a better microscope. But after a while, that stops working. And you can't use the microscopes anymore. What you're going to need to do is you're going to need to use an electron microscope, you may have seen. And then to look even smaller, you need accelerators. And that's what I want to demonstrate, why we have to do that right now. So what I have, let's see. Well, these are the sources. Let me go forward and show you why we have to do that right now. So what I have here is something hidden under this box, some things. We're going to pretend like this is a proton or something that we want to see there. And we're not going to be able to use light to look at it. We're going to use an accelerator. We're going to bounce things off to try to see what's inside there. And so the thing I'm going to bounce off it, it's not photons, they're too hard to see, steel marbles. Okay? So I'm going to do the experiment. I'm going to throw a bunch of steel marbles down at this thing, and I'm going to look at what comes out the other side. This is kind of the way an accelerator works, or an electron microscope. And so I go like this. I release them. Well, and they scattered around a little bit more than they were supposed to. But you kind of see down here. Sorry, these guys jumped their things a little bit, I guess. It must be like that. All right, but that happens. They do that in experiments, too. They just fix them sometimes. And so now what you need to do is you need to tell me how many objects are hidden inside this bar. And so by looking at the experimental results there, I'll push go. And the idea, when you're using these things, you should talk to the person next to you, because it's a great opportunity to demonstrate that you're smarter than they are. And so you always want to do that if you can. All right, figure out what you think the answer is. Erica, can you set up the next round of it for me? Yes. The question is, how many objects are hidden underneath that board? Because you saw the marbles come through. You see this pattern of the marbles. It's kind of the way a detector works, where you see what comes out and decide what's inside. Good question. Okay. And so we'll go 15 seconds. We see the results are coming in. See, 1, 2, 3. I'll show you the result. Oops. Let me do this. There you go. Now you can see about what you're seeing, and you can't change your answer anymore. Sorry, a little bit too late. And so if I looked at this, I would tend to say 2. That one marble got stuck there. But if we did the experiment a bunch of times, we'd see that this one actually would fill in 2. You see 2 holes there, so it would be natural to assume that there are 2 objects there. So that's a reasonable thing to do. But then what you might do is you might redo the experiment. This time, instead of using big marbles, you might use smaller marbles. Okay? And I'm going to use the smaller marbles now. Hopefully, I can do this without them jumping all around quite so much. Wait, let me clear off my last experiment. Okay, get rid of these and do the new experiment. Okay. And what do we see? Oh, it didn't work very well. That's what we see. Too big of an angle. Okay. So, shoot. That's too bad. So we'll do this. Now you can see what they bounced around at the bottom, so I didn't have a very good detector design down here. See, there were actually 4 things there, but the big marble couldn't fit through between these. So when you did an experiment with big marbles, this one got stuck too. If you do an experiment with small marbles, you can see that they can get through. And this is basically the way the experiments go. And there's an important physics principle going on here. So it's 4 could be a reasonable thing to say. But in fact, what you really say is you can't tell. What you can determine is you can tell how many objects there are of a certain size. And it basically depends on the size of the marbles that you're using for your experiment. And this is the reason that the next slide is going to give you the reason that we need to use high energy experiments. So can you give me all 3 screens again? Let me go back here. So when we look at how we can look at things, the reason optical light gives out is the photons are a certain size. And it seems small to us, but in fact, to a high-energy physicist, they're actually very, very large. They can only see things down to like a micron. Then you go to something, a smaller marble, which you can produce basically with electrons. You can see things smaller. A smaller marble, which you get from some alpha decays, basically helium particles. And then finally, to do high-energy physics, You use electrons and protons, very, very high energy, because they are essentially very small marbles that you're shooting things at. So that's the reason. So let's zip through this. We already did those. Okay, we've seen this animation. Great. Here. And so what we get when we use high energy is the following things. Now, the scale that I'm going to use is kind of a strange scale. I'm going to use something called an electron volt. Hopefully the word volt is familiar to you, because a typical battery is like 1.5 volts. The AAA battery is 1.5 volts. The unit of an electron volt basically says how much energy would an electron have if you connected it to a 1-volt battery, if you let it zip through a 1-volt battery. Okay, that's the unit we're going to use here. Now, we don't use 1-volt batteries. We usually use batteries on the scale of 1 with 11 zeros after it, which is like billion-volt kind of, and they're not actually batteries, but it's equivalent to like a billion-volt battery. And then you can make things with very, very small wavelengths. The wavelengths, it's like 10 to the minus 7 meters divided by the energy of that particle. And so the reason we go to high energies is because we see the wavelength gets smaller if we have big energies. Also, you're going to find out the time scale gets much smaller. We'll see later why that's important. You can take a snapshot like a strobe light, the very, very short time scale when you go to high energies. And then another thing you can do is there's this wonderful expression E equals mc squared, and basically you can produce very interesting new particles if you have enough energy to do it, using E equals mc squared. So the more massive particle you want, the more energy you're going to need, and that's going to be important. Okay, so where do you get high energy particles from? Well, it turns out there's a great place to get them from, and that is just straight from nature. Always a good place to get things from. And so this little animation here is to represent that we have protons coming at us from outer space. We're being bombarded with them. They're very high energy. They're high energy. Some are very high energy. They collide with the atmosphere and produce lots and lots of other particles with them. And so I can show you, I'm not just making this up. It's happening right now. Let's see, high or low. And what we have here is a cloud chamber, and if you look at the screen here, look for these tracks. You see a little trail. There goes one. I should use this screen too. There's little bubbles, little trails of bubbles. There was a good one. Those, in fact, are the result of protons colliding with the atmosphere, creating lots of new particles. They're cascading down. When they go, there was a good one. They go straight through there very fast. That is, in fact, basically high energy physics going on, and you can observe them in things like this. And this is the first way people are able to do sort of these high energy experiments where you can look at things at a very, very small length scale. Okay. Good. So let's stop that. People start getting nervous when they think about all those things because, of course, they're not just going through that box there. They're going through you too. Okay, so we did that demo. Good. So basically, we're back to the 1930s when everybody was basically happy. There were a few things we didn't understand, but the model seemed really, really good. And then, I don't know, exciting things happened. We can decide if they were good or bad things. But people started looking at things. They discovered the positron. We'll talk more about that in a little bit. Whole bunch of new particles. And they also learned how to make their own accelerators. They learned how to, instead of relying on outer space to send these things where, we watch, but you don't have very much control over what comes from outer space. Try to do your own where you have more control over it. And the following things started happening. Our nice thing of a neutron, a proton, and an electron started getting clouded where all these other strange particles started showing up. Pions, sigma, kaons, rhos, all kinds of stuff came up. And in fact, remember, most of our motivation for doing this is we want things to be simpler. It was going pretty good when we got down to the neutron, the proton, and electron. It was getting simpler. And everybody had the expectation that if you just look a little bit closer, it'll get even more simpler, Okay, I'm not an English teacher. But anyway, it would get very, very elegant and beautiful and simple. And in fact, what they saw is just the opposite. It started getting complicated and becoming a mess. And in fact, Willis Lamb, he got the Nobel Prize in 1955. In his acceptance speech, he made the following things. They used to be rewarded by a Nobel Prize. Now they should be given a fine if they find new things. Because it really is a very frustrating time. I mean, it's exciting, but, you know, it's exciting. So exciting can be good and bad. And people were really confused, you know, because there's, I guess the world doesn't have to be simple. All right? There's no law that says everything has to be simple. But somehow we have this feeling that there should be a nice, elegant solution to it. And fortunately, people came up with a very elegant solution, and that's about what I'm going to show you now. And it really solved all these problems, and it's just incredibly beautiful. In fact, it might be too nice. So here's what they figured out. They decided that the world is not just made up of protons and neutrons. There's something smaller than protons and neutrons. And then there's electrons, of course, too. So we're still happy with the electron. That's still our friend. But we decided that the protons and neutrons aren't the smallest thing. In fact, the proton and neutron are made up out of quarks. And so a quark is, in fact, an up, a down, and an up. I'm sorry, a proton is an up, a down, and an up quark. So an up quark has charge plus 2/3. A down quark has charge minus 1/3. So if you add these up, you get 2/3, 2/3, minus 1/3. You get charge 1, just like we need to do. And then you'll see something nice. The neutron we can make out of these same two quarks. I mean, we put 3 of them together, but this time we put an up and 2 down. So you get plus 2/3, minus 1/3, minus 1/3. So now our two things, our proton and our neutron, they're not fundamental, but we have something sort of just as elegant underneath it describing how these things work together. And the nice thing is this is going to be able to explain not just the proton and neutron, which we are fairly content with, but it's going to describe more. Then we say that the forces that we know, and now at this point we know that there's there's gravity. We're not going to talk much about that today. But there is also other forces. There's the electric force, magnetic force. They know that there's something that causes the decays. They call these the weak force. There's something that lets radioactivity occur. And then they figured there's also got to be something that holds these together. And they described them all by bosons. So we say that these things here are fermions. They make up the matter. And then bosons transmit the forces. And so I wish those lines would show up better. So this is supposed to be a picture of 2 electrons coming together. They have a repulsive force. And you can think of that force occurring by a photon being thrown from one to the other. And that makes them go apart. So I actually did these backwards. This is supposed to be, I drew a proton decaying to a neutron here. In fact, it's the neutron that decays to the proton. And I just realized that you learn lots of things when you stand up here instead of in your office. Anyway, it's supposed to be a neutron going to a proton, but the mechanism is basically the same as you see. Because a proton and a neutron, they just differ. To go from a neutron to a proton, you just need a down quark to turn into an up quark. Okay? And so we actually don't see protons decay. We see exactly the opposite thing happens. A neutron is going to go to a proton. But here you kind of see it goes like that. And you have an up quark turning to a down, or a down quark turning to an up. And that was the W that was sitting right here that makes that happen. So that's kind of our picture, what's going on. And this little guy here, called the neutrino, is a great triumph on physics. This is an example where this neutrino, it turns out you can't see, or certainly they couldn't see back then. And they kept seeing these experiments happen that seemed to violate Newton's third law. Newton has F equals ma. Well, he has 3 laws. One of them says, if I push you, you push back equally hard. And they kept seeing these reactions that it looked like were violating that. And so what they did, I mean, this took great audacity. They said, well, there's another particle. You just can't see it. They just made up. You know, sometimes I have imaginary friends and stuff like that. Well, they had imaginary particles that they just said, well, I don't know what it is, but I know, I learned in physics, Newton's third law, I believe it so much that there has to be another particle there. And it took a while, but eventually we were actually able to discover it, and that's the neutrino. So it's amazingly successful. But remember, so far I've just told you about the proton, well, the neutron, the proton, and then the neutron decaying to a proton. We explain all that stuff. That's pretty good now. We also can say that there's a strong force that holds this thing together. We have this force that holds the quarks together, and in fact, it holds a bunch of protons together in the nucleus. It's got to be strong because it's overcoming the positive repulsion of the like charges. And we have that there. We describe it with a gluon, which is pretty nice. All those things are nice, but we still haven't explained all those other particles we've seen. And in order to do that, we have to add to this family here. Instead of just having an up and a down, we added, well, the first thing they added was a strange quark, because they said, my, these are strange events. And so they said, okay, there's a strange quark. They saw more charm, bottom and top. And we have what we call 3 replicas, 3 families here that are all very, very similar. These guys over here, as you go to the right, are heavier, so we don't see them staying around very long. They often decay down into these smaller things, but they're all there. So we have 3 families, and now all those crazy particles you saw, you can produce just by combining these quarks together in different ways that are allowed, and you can understand. And once again, we have a very elegant theory. Actually, it's even nicer than this, because what we found out is that not only do we have these fermions here, each of these fermions has a partner. It's an antiparticle. Okay, so the electron, which is right here, has a charge -1. Well, it turns out there's the antiparticle, you see in the mirror here, that's called the positron. It has charge +1, the same charge as the proton. Has the same mass as the electron, but opposite charge. Everything else is opposite about it. So for those of you who either read like the Da Vinci Code and Angels and Demons, that kind of stuff, they talk about CERN, they talk about antimatter, or if you see old Star Trek things where they talk about the matter, antimatter, warp drives, things like that, then that's, well, the warp drives aren't true, or you're not allowed to know about them yet. But the antimatter is true. They really have it. The positrons are here. That's all those things there. They really exist. In fact, they make a whole bunch of it up near Chicago right now, and we'll talk about that in a little bit. So it's really a spectacular theory. It's very elegant, simple idea, repeated 3 times, explains everything we know and everything we've seen. In fact, it might, well, one of the things that we find difficult is it seems to work for everything. So here's the good news about the standard model. It is, I'm going to say it's the most successful theory in physics. Okay, so if that shows up on your physics exam, that's what you should say. Standard model is the most successful. And why can I say that? Well, it's been tested over 30 orders of magnitude. That's, you know, a 1 with 30 zeros behind it. And there's nothing's even supposed to be valid over that large of range. This is really, really incredible. And we can explain it from the photon being, mass being tested close to 0 down to here, all the way up to the tevotron energies. And everything they see fits exactly with the model. And they have looked really, 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 really hard, because there's a Nobel Prize in it for somebody that finds something that doesn't match with it. There certainly is. The other nice thing is you have these great graphics. So here's that thing I showed you before. You can make the quarks into interesting characters, the leptons, and then these bosons. Remember, these are responsible for the force. So the photon gives you the electric force and the magnetic force. The gluon, that's the one that holds the quarks inside the proton and holds protons together inside the nucleus. So that's the good news. Anytime somebody says, I've got good news, you know the next statement. There's bad news. The bad news is there's this beautiful theory with great graphics. Everything I said is true. The bad news is we can't solve it. Okay, so here, this is the Qcd Interaction Lagrangian. You should write this down. And, okay, maybe it doesn't look so bad to you, but it turns out mathematically this is not just difficult to solve. As far as we know, it's impossible to solve. Nobody's proven it's impossible, but lots of people have tried really, really hard. And in case this doesn't look bad, I took this actually from a summer school slides. It's actually worse than that. It looks more like this, okay? So this is what some kids had to do over their summer vacation in Switzerland, is look at something like this. So it looks really bad, but the beautiful thing is physicists are very smart, and they're very smart in the following way, and this is good advice. If you're given an exam question and you don't know the answer to it, okay, and it's not one of those multiple choice ones, it's a real exam question, what are you going to do? Well, don't just say, well, I don't know. What you do is you turn it into a question you can answer. Okay? Right? And answer that and hope for partial credit. So, that's exactly what physicists did. Now, you got to see. So, here's this Qcd Lagrangian, the interaction Lagrangian. I want you to take your clicker and guess which one they said, okay, I'm going to solve the hardest thing I can solve. Which one of these do you think physicists were able to solve? Talk to the person next to you, figure out which one. You can kind of tell. You're used to covariant derivatives, right? This is a completely antisymmetric tensor. Is that? Yeah. Okay. So go ahead. I'll just give you. If you can't figure out which one we could solve, remember, think about this. I mean, I tried to solve this, but I mean, there are the brightest minds, I think you can argue, on Earth trying to solve this problem. So figure, well, let me just show you what you guys are saying. Going for E. But I mean, we're talking about people who, math is just nothing to them. I mean, it's simple. So in fact, it turns out that's the answer, E. That's what we know how to solve. You did a good job. Okay, so we can't solve this. It's impossible, as far as we know. Even with computers and everything, we can't solve it. They say, what can we solve? And we say, well, if the interaction Lagrangian, that means if the particles didn't interact with each other at all, we can solve it. That's not such a hard problem. Basically, particle starts in a straight line and it just keeps going. Okay? And we can write that down mathematically. It's very elegant. We started with that. That's what we can solve. And from there, we're able to have the best tested theory in all of physics. Well, in all of science, I think. Okay? It's kind of an amazing thing. And so how do they do it? Well, there's this great guy, Richard Feynman. So if any of you need fun projects to do, to write about somebody, this guy has no end of interesting things that he's done, from working on the atomic bomb to the space shuttle. So he's done lots of stuff. And basically, what we've drawn here is this picture. Here's the picture that I showed you, the graphic of what's happening. And they said, look, if you just pretend these electrons are basically free and zipping along, and then once in a while, they'll see another one, and they'll bounce off each other a little bit. We can do that calculation. It's called perturbation theory. You say it's basically free. They're just a small interaction as long as the force isn't too strong. It turns out that's okay for the photon here. And in fact, this picture I drew to show you how this thing happened, he actually came up with this idea that he could draw pictures for all the different things he could imagine happening. And then he could put mathematics to this from basically going back from the previous Lagrangian equation. He could put mathematics to it and give you the calculation. So now when we do high energy physics, what we do is we draw these pictures, and then with each piece of the picture, there's a little math thing that you write down. And these things go in the numerator, those things go in the denominator. You really just write them down, and then you solve it, and you get your answer. And so it's very elegant. This guy is a very, very interesting character. And this is the basis on which we have the best tested model in all of science. So remember, we need high energies to get small distances, short times, create exotic new particles. We're not just going to wait around for particles from outer space, though. We're going to create our own. We need high energy colliders. So we're going to go here from Loomis Lab, and we're going to go across to California. Yeah, the slack. So we're going to go down here, zoom in here a little bit. That is the Stanford Linear Accelerator. Remember when I said these electrons, you speed them up by connecting them to a battery. But if you make your battery too strong, too close together, basically you get lightning, right? And that doesn't work. So there's a maximum rate. Oops. great. Here's a little better picture. So here is the Stanford Linear Accelerator, and you can start these things down here, and basically you can think about them as sliding downhill to get going faster and faster and faster. Okay? And basically, if you want them to go really fast, you need a really big hill, and there's sort of a limit to how steep you can make things. So that's limiting things here. This is about 2 miles long, and it does a pretty good job. It gets you to pretty high energy. Sorry. It will get you to pretty high energies, but you see there's a problem with it. You can only make things so long. It gets very, very, very expensive. And so lots of good stuff was learned there, but I want to move you forward. And now we're going to go east. We're going to go to Geneva, Switzerland. So we got to cross the ocean and come on down here. There we go. And so we can go to Geneva, Switzerland, and we're going to look at a very nice large collider there, but this one they made a circle, and you can almost see it. There's a circle here, and the beauty of a circle is if you send the thing around in a circle, each time it comes around you can give it a little push and get it going faster and faster and faster. Let's see if we can see that here. Here it goes around. Well, that wasn't that much faster. It's supposed to go a little fast. There we go. Now we got her going. Okay? So it goes around, and each time you give it a push, and it goes faster and faster and faster, so you can get higher energies without building it so long. But, as with all things, there are limitations to how fast you can get it going. And in this case, the difficulty that you have is, as this thing turns around, it gives off photons. Electrons like to do that. It radiates, and so after a while, it just doesn't go any faster. And so you have to make the loop pretty big. The wider you make the loop, the less angle you have, so the faster you can make it go without it radiating too much. And so you can get pretty high energy, and they did this. This was Large Electron Positron Collider. It's 27 kilometers around. This is just to show you some of the things they see. These are pictures like we saw from the cloud chamber, but much more sophisticated electronics to see things there. But now I want to bring you back close to home. And this is, you see, there we are. But we're going to go up here near Chicago to Fermi National Accelerator Laboratory. So there it is, right there. You can see that ring. Oh, I didn't tell you. The one thing that was boring about the one in CERN is it was all underground, so you couldn't see very much. Fermilab's much nicer because you can actually see the rings from the air up here. So you can see the stuff going around. We'll go closer. And here's what they have up there. Nicer picture here from an airplane, I think, instead of a satellite. But you can accelerate these protons. Now, in this case, they're still worried with these electrons. It's hard to give the electron a lot of energy, basically because it's so light. It's hard to make it spin around. So what they did is they used something heavier. They used the proton. Proton's 2,000 times heavier, which means you can give it more energy, basically, in the same size. You can give it more energy. And so they chose to do this, and they have 980. So GeV, that means it's 980 with 9 zeros after it. That's a big battery, right? And so, in fact, they don't get that from just one. They don't even get it from just one ring. But basically, you get it going, and then you get around the other thing. More and more energy as it goes around. And then you collide protons, and here's the beauty of it. You collide them with antiprotons. So antiprotons, a proton is made up of an up and up and a down quark. An antiproton is made up of an anti-up, anti-up, anti-down. So it's matter, antimatter. It's truly whatever science fiction you might think, that's what it is. Okay, they really do that, and they do it all the time, and they do it really well. And so that's really good. They get up to very, very high energies here because they have a much heavier object. Of course, there's a price to be paid in that you're not just accelerating a simple electron. You have this proton here, and you don't know if you remember. The only reason we were able to solve these calculations was because the only reason we could solve the calculation was because we said the interactions were weak. We said L equals 0, and then a slight fix to that. Well, we know that the proton is held very, very tight together. It's a very strong force. It's not small at all. And so that's a little bit of a concern. And this picture is okay of the proton if you look over a long time. But in fact, the proton is a much, much more complicated beast. You can see our up, our down, and our up quark inside the proton. But in fact, and that's what you see. This is what you see if you look over long time scales. But if you look at very short time scales, there's lots of stuff going on in there. Okay, there's lots of stuff. And let me try to see something. So there, you saw a D and a D bar just kind of created and disappear again. It really happens. They measure it. They see it happening. It happens a lot. And the quicker time scale you take a picture of, the more detail you see. So I have a little demonstration here to maybe illustrate that a little bit. Did that? Oh, wrong computer. There we go. And so now let me turn out the lights. This one? No. Yeah, I think I just turned them out. Okay. And so you can think, remember the proton, oh, I didn't actually tell you this, so you can't remember something I never told you. But turns out the way the proton works, there are three colors for this strong force. There's red, green, and blue. And so two different colors attract each other, two of the same colors repel each other. So inside the proton, you always have a red, a green, and a blue quark. And then if you were to look at it over a long time scale, you would see something like this, where it looks white. But if you were to take a snapshot, you'd actually see the three different colored objects. Okay? And so that's one of the beauties of doing very high energy. We're taking such short pictures that we can actually see sort of the individual colors of the things that are going on there. I also did this just because it's pretty. So this is just totally gratuitous here, but I do that in my lectures too. So if I do this, it should be a pretty pattern. Okay. They don't actually do that at the colliders, but it's kind of cute anyway. Okay, so let's get back to our program here. So this is potentially a problem, but because they're going to take a picture so close in time, even that strong force is not going to be an issue. And here I have an event for you to look at, and I lost my second laser pointer. How many am I given? And so let me start this up. Oops, go back. Let me show you a picture here. This is going to be, that's a proton and an antiproton. They're going to come together. They're going to collide. Tell me if you can figure out what they make. There you go. Did you see that? Okay. So it's a real simulated event. Means that, like, it could have happened, and it probably did happen, but I can't prove it. And so here we go. We have the proton, antiproton coming together. These are the remnants coming out. You see all this goo coming out. All that goes out and gets caught in the detector, kind of like we saw these marbles down here. And from that, they figure out what's happened. So you couldn't see that very well. So let's take a closer, slower look here at it. So I'm going to do this again, a little bit slower. And now here you see this is the antiproton and the proton. Watch this quark and that quark collide. They produce the top and a T-bar. Those turn W and a B. They go off. And now what you're going to see is this charm and this strange. One's red and one's anti-red. And as you try to separate them, that force gets really, really strong and actually gets so strong that it creates a bunch of particles in between there. And it's kind of ripping the thing apart. And these things are going to go out. And these are going to combine into, these two here, for instance, will be a pi plus, one of those objects. They combine into pi, and those go off to your detector. Okay? Took me about 3 months to make this, so you're going to watch it a few times, okay? So now that you know what's happening, here it goes. So this is just one collision. These two guys are going to take place. The other guys are just going to go along for the ride. And essentially, it all happens so fast, they don't even know what happened. They just keep going out there, and all this other goo comes out. Okay, so that's what one of these, that's a simulation of what one of these events looks like. And I won't really make you watch it any longer, I don't think. I guess I can't help myself. Let me try. I guess maybe I have to stop it. And then we go. So, it turns out that that event I showed you, they actually saw several of them up there at Fermilab. Our own was instrumental in analyzing the data. So the data looks something like this that they have to figure out. Turns out 1 in about 10 to the 10th collisions actually gives you an event like this. So it's a lot of work to figure out which events they are, figure it out quickly, and then this is a beautiful graphic they made of it, of the things colliding, the T and the T-bar coming out. But they did that, they discovered it. A cool thing about it is it's 175 times heavier than a proton. So the proton, which is not fundamental, it's made up of 3 quarks. Here we have something we think is fundamental, point-like, and it is 175 times heavier. It's very intriguing, and it leads us to believe there's some interesting things happening. This is what the detector looks like up there. Of course, it's very big. You have to be big in order to deal with numbers like this of things happening. So they have huge numbers of events coming through that they have to quickly narrow down to the ones they can store on the computer, which is about 50 a second. And Kevin Pitt's actually the one who introduces this thing. He actually built this detector. Well, he built pieces of the detector, okay, and is responsible for them. So here's a quiz for you. The size of the beam pipe that the protons and antiprotons go in are about the size of this laser pointer, okay? The detector is around it. So what I want you to do is figure out how far away, if the proton was really this big, like I drew it here, say 1 centimeter, where would the detector be, the closest part of the detector in terms of trying to see this top quark event? How far away would it be? Would it be out in the hallway? Would it be in Savoy, lower taxes, out in New York, Mars, Alpha Centauri, which is a star? That's just your biggest answer there, okay? It's a long way away. So go ahead, I'll start the thing, talk to the person next to you, see what you can do. There you go. How did you know that? No, that's not. Oh, very good. Okay, yeah, it is. All right, so I'm going to, let's see how we're looking here. Okay, yeah, so we got a nice distribution here. People are thinking pretty far away, and that's exactly right. So the simulation that I made before, where you saw those things happening, I'd wanted to put the detectors on there. But in order to do that, the first edge of the detector shows up. No, yeah, there it is, Mars. It's really far away, so it's kind of a dull video because basically you see that stuff happen too fast, and then, if you slow it down that much, you basically, have to wait about 20 years before it actually gets to the detector. And the reason I point that out is it's just amazing that they're able to do. I'm a theorist, so I can't take any credit for it. It's amazing they're able to measure things the way they can measure them when basically the difference in scales is so enormous from what we're capable of actually touching to what we have to infer about. The beauty is the best is indeed yet to come. And so I talked about 3 forces. Strong, that's the one that holds the quarks in there. Electromagnetic, that's the photon. Weak, that has to do with the neutron decaying into a proton. And if you look at how these forces change as you change the energy, the strong force gets weaker, the electromagnetic gets stronger. It's kind of, it's like, hey, maybe I don't need to know 3 things, maybe I only need to know 1 thing. But we know that the standard model is incomplete, because, in fact, if I draw these lines the rest of the way, they almost intersect. I mean, 2 lines intersect, but they don't all 3 intersect at the same place. So they almost work. The other thing I know is if I do some of the calculations just with the standard model as high energies, it's clearly wrong. It starts giving nonsense answers, things that can't possibly be true. So we know it's not right, but we can't figure out what's, all our measurements keep agreeing with it. And, we keep trying to go to higher and higher energies to figure out where is it going to go wrong. But the theorists in this case kind of got ahead of the experimentalists a little bit, and they said, well, it'd be cool if these things matched up. And there's this idea of supersymmetry that says not only does a particle like a quark have the antiquark, but it has a supersymmetric partner. I think we can make a nice graphic for that, can't we? Yeah, there we go. A supersymmetric partner on the other side, and because you have this difference between fermions are matter, bosons do forces, well, you take for every fermion, you get a partner that's a boson. And it's pretty cool. I mean, if it's true, it's that like half the particles that are allowed in the universe we've never seen, or we don't realize we've seen them if we have anyway. And it's a very so that these three graphs come right together. So it must be true, right? I mean, but it does make us very excited. It also makes our calculations work out at much higher energies where they didn't seem to before. And the beauty is, this is all going to get tested soon. They're trying to find it in Chicago at Fermilab, but the energies are a little too low. They're building a new collider, actually at the same location that they had this big electron one. Now they're going to put protons in there. And because they're protons in the same size space, you can get much, much higher energies. And so they're going to go up to about 7 times higher than what they can do at Chicago. And do that well, that's not, we don't need to watch that go around. And when they do that, the calculations all say they're going to find something. Something has to happen there. We know our thing won't work. And so there's lots of big things they build to go there. This is a tunnel. Just if you want to see, there's not much curve in a tunnel that's 27 kilometers long. It looks pretty straight. And inside there is where the protons will be. And it's going to turn on in 2008, which means we're going to have some very exciting results coming out. So, you've made it. Here's what you need to take away if you have to give a summary to your physics prof. High energy is required so that you can see things at very small scales. The standard model is absolutely amazing, the best tested thing we have, but it's also incomplete. We know we're missing something there. And there are going to be many new discoveries coming soon, around 2008. Okay, that's it. Thank you so much for your attention. Oh, I have to give one announcement. There's about a year's worth of my salary, yeah, over $400 worth of clickers out there. So I need these back, okay? What? Oh, you don't care about that bill, do you? We'll talk afterwards. We'll figure something out. I see he had forgotten. Come on. Okay. So yeah, we can talk about questions. Can we talk about questions? If anybody has it, sir.
You say you're missing some matter, missing something. You have matter and you have antimatter.
Yes.
You make an analogy to an atom. You have a proton, an electron, and you have a neutron. Maybe you're missing something neutral.
Ah, okay. Yeah, an interesting question came up and said, well, let's learn from history a little bit. If you look at the atom, you have the proton and the electron, and she's kind of comparing to matter and antimatter because they have opposite charges, and so we'd say opposite fermion number for matter, antimatter. And then there was a neutron, was an important part of an atom. Maybe we have the same thing that we're missing in, this supersymmetry idea. And is there an analogy to that? And it's a very interesting idea. And I don't think we...
You said you were missing about...
Yeah. Oh, the comment of not seeing half of them is like we don't think we should have been able to see them is the thing. Our energies are too small. But we will now when we go a little bit higher, and we'll see something, and the question is, what do we see? Something has to happen there. And what I describe supersymmetry, it might be something different, which would actually be even more fun, to be honest with you. Great question, yeah.
Like in this month's astronomy magazine, they were talking about matter and antimatter and like when it collides.
Yes.
They were saying that makes it gamma ray bursts.
Yes. Okay, yeah, so an excellent connection was made in, I guess, this month's astronomy magazine. They had talked about matter and antimatter coming together and producing a gamma ray burst. They collide. And that's exactly right. Matter and antimatter come together like happens at the Tevatron up in Chicago. They, in fact, exactly combine and produce energy. They annihilate into energy which could be a gamma ray burst, and it can produce lots of different things, but including the gamma ray burst. It is exactly the same phenomenon. That's exactly right. Good. Any other, sir?
When you were showing the proton and the three parts, did you say the force of those three parts is stronger than the proton itself?
Okay, so the force between these three quarks is stronger than the proton itself. It is what holds the proton together. It's a strong force. It's what holds the proton together and actually holds multiple protons inside the nucleus. So I can't say it's stronger. It is the proton, exactly. Great, good questions. Any other questions? Yes, sir.
So the protons, why they don't repel each other, is that?
Oh, this is, okay, repel each other. They have like charge, so they should repel each other. In fact, they do. The protons do repel each other. It's just that this strong force is so much stronger. And if you look at the periodic chart and you look at how things go, pretty much you see the same number of protons and neutrons as you go up. But when you get to high values, all of a sudden the neutrons start getting ahead. And the reason for that is because the repulsion from all that positive charge becomes an effect, and you start noticing it. So excellent, excellent connection. That's exactly right. Yes?
When you had the decay in the cloud chamber of two protons and antiprotons
Yeah.
hitting, and then they made the other particles.
Yes.
Were the quarks changing them? Are the quarks not fundamental?
Oh, okay. Really, really good question. Okay, so that's two good questions. Yeah, yeah. So let me take one first. Are the quarks not fundamental was a question. Like the quarks and even the leptons might not be fundamental too. And as I said, as this demonstration was meant to show, all we know is that they are fundamental to the scales that we can look, to the smallest energies that, or smallest distances that we can probe them. So we have some limit on them not being bigger than a certain size, not being made up of other things that are a certain size. But as we go to higher, yeah, you know, they could be made up of something smaller, but it would have to be really, really small. And we don't think that we're going to be able to, well, there aren't people expecting to be able to see that. They expect to see supersymmetry will be easier to see before that. But it might be true. I'll come out of it. The second question is, do these quarks change? And absolutely, they do. And there's this, I don't have it up here, there's this W boson. The way we can make a neutron go to a proton was, in fact, by an up quark to a down or a down to up. And in fact, they can jump across here too. It's just less likely. And so they can switch different things. They absolutely can. Great question. Any others? Sir?
What's the bottom line for all this science? Since all this is discovered and everything, we got all this stuff going through us right this very minute.
Yes.
Is the idea that maybe when you do all this, besides bombs, are we going to get energy out of this, or produce electricity?
Right. Really, really good question. What's the bottom line? I started by saying smaller scales, better energy. I think getting energy out of this directly, you know, always you're looking way off into the future. But the better you understand things, the better you can make it happen. So for instance, on the nearest scale, people talk about nuclear fusion instead of fission. Fusion as being a great energy source for being able to do that. And the trick to fusion is you got to get those two guys, those nuclei really close together before it'll happen. And so you might imagine that if you understand things better, maybe you can get some sort of catalyst that would somehow, you know, overcome the repulsion. I mean, I'm totally making this up. There's not something else. But always, the better you understand things at these smaller scale, the more likely you're able to make it, to manipulate it to work for you. And, you know, there are enormous possibilities there if you can do that. Good question. But again, I think most of us are motivated for the understanding reason because we believe that practical applications are a fair ways off. Okay.
Great questions. Thanks.
Great. Yeah. Very good.
I would encourage you to maybe, if you have more questions, to come down front. You can also come down and take a look at the cloud chamber if you're interested in seeing that anymore. It's pretty cool to see cosmic rays after they pass through the cloud chamber. If you still have eye clickers, we'd appreciate it if you could just drop them off on your way out. We have a little box back there in the back so that we can have those back. We We hope to see you again. Have a nice Thanksgiving. We hope
Yeah.
to see you again in 2 weeks for Jim Wolf's presentation. And let's thank Tim one more time.